Hi there, everybody. In this video, we're going to talk about the ellipse. The ellipse is a special geometric curve that comes about in a special way. It comes about from taking a cone, and this is a double cone. It's a cone with two tips touching. So you basically take a line and you swing it around and you form this cone. And if you take that cone and you make a conic section, and you make a conic section by intersecting this cone with a flat plane. Depending on the angle of that plane, you'll get either an ellipse, a hyperbola, or a parabola. So an ellipse is one of the three conic sections. Now there's another way an ellipse comes about, and that is by picking 2 points and taking a string of a fixed length and then attaching it to those 2 points and then just tracing out a shape by holding that string taut. And if you do that, you will get an ellipse. Now, one thing we might be interested in is the equation for an ellipse. So what we're going to do is we're going to first derive the equation for the ellipse, and then we're going to take a look at some of the geometric properties of the ellipse. Okay, so let's go down and derive the equation of an ellipse. All right, so let's find the equation of our ellipse. So I'm going to do my best to draw an ellipse. All right, not too bad. It looks more like a potato, but we'll pretend like that's an actual ellipse. Now I'm going to center this ellipse at the origin, okay? And remember how we can define an ellipse. One way is by taking 2 points, attaching a string to those 2 points. So let me pick the points here. Those points are going to end up being equidistant from the center of the ellipse. All right, so I'm going to label these points negative C0 and C0. Let's just pretend like these points happen to fall on the x-axis, and the center of the 2 points is where we put, it happens to be where the origin is. Okay, we can always reposition the ellipse so that it ends up here. All right, and what we do is we take a piece of string and we tie it between these 2 points, and then we hold the string taut. All right, so I tighten the string up, and I'll find myself at some position in space out here. And if I keep the string taut and move my finger, keeping the string taut, I will be forced to trace out this curve that is the ellipse. All right, so this point here, let's call it x and y, we need to find an equation for these coordinates x and y. That'll be the equation of the ellipse. Now, because the string has a fixed length, we know that this distance plus this distance is the length of the string, and that's always a constant. All right, so d1 plus d2 is always a constant. All right, so I'm going to represent it by a letter. So what I'd like to do naively, if I was just coming at this the first time, I might just represent it by the letter A. But I know how this is going to play out. I've actually done this before. And I know that it's better if we represent it as 2A. All right, so I'm going to call this twice A. Or in other words, the letter A is representing the total length of the string, d1 plus d2, divided by 2. All right, so it's 1/2 the length of the string. All right, so if A is half the length of the string, then this equation makes sense. And A is a constant. The string has a fixed length. Okay, so what we want to do, though, is we want to have an equation that involves x and y. All right, well, how do we get that? Well, we happen to know a formula for measuring distance, right? We know that to measure the distance between 2 points, what I do is I take the difference of the x coordinates, square it, and add the difference of the y coordinates, square that, and take the square root. That gives me the distance. So I can represent d1 that way. Now, if you don't believe me about that, it's very simple to see that. You just draw a right triangle. Just drop a line vertically down here. That makes a right triangle. Okay? And we know from the Pythagorean theorem that d1, being the hypotenuse, is the square of d1 is the sum of the squares of these two sides. Well, this side is just the difference of the x coordinates. It's x minus negative c. And this distance is just the difference of the y coordinates, y minus 0. Right? So if I square this and square that, that'll be the square of d1. So d1 is the square root of that. So that's where the distance formula comes from. It's just the Pythagorean theorem. All right? So let's write that down. And what's d2? Well, I do the same thing. d2 is the square root of a sum of squares, right? The first square is the difference of the x-coordinates, x minus c, so I get x minus c squared, plus the difference of the y-coordinates, so y and 0. So y minus 0 is just y squared. So I applied the distance formula, I got these. All right, well, what I'm going to do is I want to get this equation looking nicer, okay? So what I'm going to do is I'm going to try to get rid of these square roots. Well, I can get rid of a square root if I isolate it on one side of the equation and then square both sides. All right, so I'm going to subtract this quantity from both sides, and then I'm going to write my equation so that this term is on the left. Okay, and then like we said, we are going to square both sides. When you square that out, you get this. Looking kind of hairy here, right? But I see something here. I see a plus y squared on each side. Well, I can subtract y squared from both sides, so wham. Those are gone. Okay? Now what I'm going to do is I'm going to multiply out these squares over here. Okay? And then I see there's some other stuff that appears on both sides, right? I have x squared on both sides, so I can subtract x squared from both sides. I have c squared on both sides, so I can subtract c squared from both sides. Okay, so now I'm going to manipulate terms a little bit more. I'm going to add 2cx to both sides. All right, so it'll kill it over here, and it'll introduce 4cx over here. I'm also going to subtract 4a squared from both sides. Okay, so now I see that everything is divisible by 4, so let's divide through by 4. Okay, and now I want to get rid of this radical, so let's square both sides again. So what I'm going to do now is I'm going to expand this x minus c squared. Okay, so I've expanded that out. I'm going to distribute the a squared through. Okay, now let's see how we can clean this up. Oh, I see. I have this term over here and over here. So if I add it to both sides, it will cancel out. Okay, so now I'm going to do some other things. I'm going to subtract a squared c squared from both sides. All right, so I'm going to have that on the left. But I'm also going to subtract c squared x squared from both sides. So that's going to end up as a negative over here. Okay, so now what I can do is I can do some factoring. I can factor out the a squared over here. And I can factor out an x squared from these two terms. Okay, so here we are. What we're going to do now is, because I see this term a squared minus c squared here and here, I'm going to represent that by a new variable. All right, we are going to let b squared equal a squared minus c squared. All right, we're going to just make this substitution. Well, now you might be concerned here. You might be saying, well, wait a minute, how can we do this? What if a squared minus c squared is negative? Then we couldn't represent it as the square of a number, right? Because the square of a number is always non-negative. So this could be problematic. It's not for sure right now that we can get away with this, right? But let's go look at the picture. Remember what a is. A is exactly half of the total distance. Okay? Well, c is half of this distance right here. Right? But this distance is always going to be less than the sum of these two distances. So if a is half of this, a is automatically greater than half of this. So we know that a squared is always greater than c squared. So this is actually okay. A squared minus c squared will be a positive number, so we can represent it as the square of b. All right, so we're going to make that substitution. So what do we get? I wrote this term on the left as a b squared, right, because I like to put the non-x's and y's to the left of the x's and y's. And I think we're just about there. I think if we just divide through by a squared b squared on both sides, what happens? Well, let's see. This stuff just becomes 1. Here, the b squareds cancel, and here, the a squareds cancel. And here we have the equation of an ellipse. Whew, took a lot of work, but we got there. Basic algebra, just basic algebra. And it got hairy in the middle there, but we persevered and we made it through, and we got quite a nice little equation here. Now, I'd like to point some things out about this equation. If a squared and b squared were the same, if they were both equal to r squared, for instance, I would have this equation. And if I multiply both sides by r squared, what does that become? I get the equation of a circle. So this is nice. This is pleasant. An ellipse is just kind of a variation of a circle. It's just stretched out a little bit. So it's not surprising that if I make some minor adjustments and arrange things just right, the ellipse will become a circle, right? So what we need to do now is explore what these parameters have to do with the shape of the ellipse. So that's what we'll do next. So here we have an ellipse centered at the origin. So what we'd like to do is describe some of its characteristics. So first of all, notice that we can adjust some of its parameters. We can adjust its height and its width. These things can vary, all right? So the parameters we describe are going to take all of these things into account, all right? So one of the things that we can try to describe are these 2 points here on the edges and these 2 points here on the top. Now, when the ellipse is centered at the origin, these 2 points on the edges are just the x-intercepts. So to find the x-intercepts, we take the equation of the ellipse, and just like with any equation, to find the x-intercepts, we set y equal to 0, and we solve for x. And you can see that in this particular case, there's two solutions. X equals plus or minus a. And so that gives us the coordinates of 2 points, a comma 0 and negative a comma 0. These 2 points on the ends. All right, what about these 2 points? Well, when the ellipse is centered at the origin, these are the y-intercepts. And as with any equation, to find the y-intercepts, you set x equal to 0 and solve for y. And when we do that, we see there are two solutions, y equals plus or minus b. And so that gives us 2 points, 0 comma b and 0 comma negative b. So now we have the x-intercepts and the y-intercepts, and we see how they're related to the equation of the ellipse. Now, there were two other points that we had in our ellipse, and those were the focus points, or the foci. Now, the foci have coordinates having to do with c. Now, we have to be a little bit careful here, because if we adjust the ellipse so that the height is more than the width, we see the foci move to the y-axis, but if the width is more than the height, the foci are on the x-axis. They'll always be on the axis in the direction where the ellipse is the longest. But how do we find the value of c? Well, we know how to do this because in the work that we did to derive the ellipse, we established a relationship between a, b, and c. And so we can use this to solve for c. In fact, if I solve this for c now, I'll see that c squared is equal to a squared minus b squared. Now, we have to be a little bit careful here because we did this in the situation where the ellipse was longer in the x direction than the y direction, and so the foci were on the x-axis. And for that reason, it made sense to compute a squared minus b squared, a squared minus c squared, because a squared was bigger than c squared. Right? Now, if we were working with an ellipse that was longer in the y direction, we would have had this whole problem set up differently. We would have started with b here, and we would have set a squared equal to b squared minus c squared, in which case we would have used a different equation. We would have used c squared equals b squared minus a squared. So depending on whether the ellipse is longer in the x direction or longer in the y direction, we would use a different equation here.